Day 162, Honors Physics, Homework Hints, Problems 25, 26, and 30. Here we have a photoelectric effect problem. The photoelectric effect equation is the energy of a high-energy photon will be transferred to or equal to the work function, the energy necessary to pry the electrons loose, so to speak, plus the extra energy left over will go to the kinetic energy of the photoelectrons. Go to the maximum value. In this problem, they're telling you what the threshold wavelength is that will match up to the work function. So we're not assuming we know the work function for gold in this particular case, but the threshold here, and I'll just do this as a separate calculation, the wavelength for that threshold is 260 nanometers. So I'll use V equals lambda F 3 times 10 to the 8th equals 260 times 10 to the negative 9th times F. That will give me the frequency of these threshold photons, and using that, then I will do E equals HF to get the energy of these photons. And let's do it in joules this time, since at some point we need to switch over to kinetic energy, and the kinetic energy always has to be done in joules. So find the energy of the incoming or the work function photons in joules. And likewise, repeat that basic process we just did here for now the high energy photons in this problem are associated with 135 nanometer photons. Now we're going to shine ultraviolet light on this gold surface. So these photons will have a higher energy than the threshold ones we just figured out. So let me repeat that. This energy here, once again, you can do it in joules or electron volts, but joules will be better, will be the work function energy for gold. And then you repeat what we have here on the right hand side. Just do V equals lambda F once again to figure out the frequency of our high energy photons, and then use E equals HF once you have the frequency from V equals lambda F, and that then the energy you get from those calculations, once again do it in joules probably, that energy will be the energy of the photons, high energy photons. Knowing those two things, you subtract those, or basically move the work function over, you will have then the kinetic energy of the electrons, which you will plug into 1/2 mv squared. In other words, you will know this goes there, and you know that the mass of the electrons, 9.11 times 10 to the negative 31st kilograms, and then you will have it. Another classic photoelectric effect problem. We have, once again, high energy photons equals the work function for the material plus the maximum kinetic energy of photoemitted electrons. In this case, we have the 550 nanometer photons. Those are the high energy photons. Those are not the work function photons. So just like the last problem, we would use V equals lambda F, knowing that V is 3 times 10 to the 8th and lambda is the 550. So we know both of those. You calculate F. Once you have F, then you would use E equals HF, because you know F from the first part, and you know H, you would calculate E. You would have a known value for E of these high energy photons. That would be on the left hand side of the photoelectric effect equation. So we'd have the energy of the photons, and that would go here. And it tells you the maximum velocity of the electrons. And by the way, you probably want to do that first part in joules once again, because kinetic energy is always going to be in joules. Stick with joules for kinetic energy. When in doubt, go to our standard units, joules. All right, so then you do the kinetic energy of the electrons, which will be 1/2 the mass of an electron, which is 9.11 times 10 to the negative 31st kilograms. times that given velocity, 3.2 times 10 to the 5th, that's quantity squared, 1/2 mv squared for the kinetic energy. So you will have the kinetic energy of the electrons, that's always in joules, but bottom line is that value will go here. Once again, if they're both in joules, I mean, you can convert them both to electron volts, then your work function would come out in electron volts, but it doesn't say that you have to use, oh, it does say electron volts. So at some point then, once you have that in joules, you have to convert over to electron volts. Probably at this point, I would do the conversion. All right, then part B. Part B, find the wavelength of the threshold. So once you have the energy of the threshold from part A, so use your answer to part A, just use E equals HF. Take that answer from part A. That's the energy of our threshold photons. And you know H, so then you will calculate F. And then once you have F, you use V equals lambda F, because you'll have that F. And the velocity is always 3 times 10 to the 8th. And then you'll get the threshold wavelength, which matches up with the threshold frequency, the threshold energy, work function. Those are all things that are associated together. Okay, example number 30. All right, we want to find the average output power of this ruby laser. Well, this is not a photoelectric effect problem. There are two things going on once again. We have the power equals the energy over the time. Now I think they give you the time here, 0.8 seconds. But we got to find the total amount. We got to find the total amount of energy in this time. Now the energy of an individual photon is E equals HF. But like previous problems, we don't have F. So the first thing you would do is use V equals lambda F. So I'm going to start way over here on the right hand side, because you know the velocity of photons, 3 times 10 to the 8th. You're given the wavelength. You calculate the frequency of those photons. Then you would plug that into here. And I would definitely do this problem in joules this time. So then you could find the energy of the photons. Just take Planck's constant times that frequency, gives you the energy of an individual photon. But that's not your total energy, that's the energy of one photon. Well, bottom line here is that the E, that's the energy of a photon. E total, the total energy here, I think you can probably see this, will be the number of photons. In this case, I'll just call it N, but N is 10 to the 30th. They give you that, 10 to the 30th, times that energy of one particular photon. That's a pretty easy calculation. That gives you the total energy. So you'll take that answer and plug it in here for your total energy over the total time of 0.8 seconds. That'll give you the power in watts. That's part A. Part B. Well, part B, you have lambda equals H over P. Once again, you cannot use P equals mv for the momentum of a photon because photons have no mass. But you can use P equals H over lambda. But that will give you the momentum of one photon. You're given in this problem, you're given lambda in this problem, and you know H. So you would get then the momentum of one photon by just plugging in those two numbers. But you want to have the momentum of the light pulse. Well, basically it will just be the total number of photons, like we did in the previous part A here. P total momentum, will be the number of photons, n, which is 10 to the 30th, times the momentum of one photon. So it's just simply taking your answer and multiplying by the 10 to the 30th, taking your first answer from the h over lambda for one photon, and that should do it for you. Good luck.